Chapter 4 Special Probability Distributions. You all know by now, depending on the type of the variable, you can have discrete probability distributions or continuous probability distributions. If your random variable x is discrete, which means the possible values that x can contain are only whole numbers, no fractions, no decimals, then we end up with discrete random variables. For discrete random variables, we end up with probability mass functions. A probability mass function contains all possible values of x and their corresponding probabilities. On the other hand, if x is continuous, it can contain any value within a given interval, the decimals, fractions, and all of them. Then we end up with a probability density function, and we end up with probability distributions for continuous random variables. In this chapter, we are going to look at some prominent probability distributions that come under discrete random variables and which are widely used in statistical theory and applications. We start with the easiest one, the basic one, which is the discrete uniform distribution. When we see the word uniform, you all know the meaning of that. Uniform means it is equal everywhere. If a random variable can take on k different values with equal probability, we say that it has a discrete uniform distribution. Here's the exact definition. A random variable x has a discrete uniform distribution and it is referred to as a discrete uniform random variable if and only if its probability distribution is given by Px is 1 over k. For x having values x1, x2 up to xk, where xi is not equal to xj. How do you get this 1 over k? According to the definition, a random variable x has a discrete uniform distribution when these k different values can take equal probability. You know that the total probability is always 1. The total probability is always 1. If you need equal probability to be distributed among all possible values of x, then you have to divide this total probability 1 by all possible outcomes k. So that is how you get your PMF to be 1 over k. For example, if you roll a balanced die, 6-sided die, if it is balanced, all 6 sides have the same probability of being selected, which means in this case k is 6 and the probability of x will be 1 divided by 6. Now let's see how we can get the mean and the variance of a uniform distribution. Okay. Mean or mu, or the expected value of x, ex, you know how to find it. That will be the sum of all possible x's, x times px. So when it is uniform, x can go from 1 to k, x times px is 1 over k. So by solving this summation for the possible values of k, you can easily find the mean of the distribution. The variance of uniform distribution, sigma square You can use the computational formula or the definition itself, which is x minus mu square, its expected value. So that will be the sum I goes from 1 to k xi minus mu square times px. So this will be I going from 1 to k xi minus mu square and px is 1 over k. Again, solving this summation, you can easily find the mean and the variance. So let's try to simplify these two expressions. Example 5.1. If x has the discrete uniform distribution where px is 1 over x for x going from 1 to k, show that the mean is k plus 1 over 2 and the variance is k square minus 1 over 12. So let's start with the definition and try to find the exact expression for the mean and the variance. Mean is the sum of I going from 1 to k I times 1 over k. 1 over k, it's independent of I, so we can take it outside the summation. Sum I going from 1 to k I. So this is I going from 1 to k, the summation of that. So if you write it, that will be 1 plus 2 plus 3 plus 4 all the way up to k. And we see that this is the sum of the first k integers, right? And we know there is an equation for that. Okay, so that will be n times 1 plus n divided by 2. So this is the sum of the first n integers, and in front of it we have 1 over k. Right. So if you use this equation in our formula, okay, we end up with 1 over k in front, sum of k integers, so you have k times 1 plus k divided by 2. This k cancels out, so you will end up with k plus 1 divided by 2. Say for example, k is 6, the mean will be 7 divided by 2, which is 3.5. Now let's look at the variance. Sigma square is sum of I going from 1 to k xi minus mu square times 1 over k. So let's expand this one. Again, taking 1 over k outside, the summation I going from 1 to k I minus mu square. Which is I goes from 1 to k I square minus 2 mu I plus mu square times 1 over k. This is the expansion of the quadratic formula here. Now let's distribute the summation over these three expressions. So you end up with summation I going from 1 to k I square, that's the first one, minus 2 times mu, this is constant, independent of I going from 1 to k, this I, plus Mu is again constant. If you add mu k times, you'll end up with k times mu square. And you have 1 over k outside. Now the sum of the square terms of the first k terms, again it has an equation. So I hope you can remember this. 2k plus 1 divided by 6. Okay, this is the sum of the squares of the first k integers. So that is the first term. Then you have 2 times mu. We found that it is k plus 1 over 2 times I. So the sum of I is again k times k plus 1 over 2. So this is the second summation. And then at the end you have k mu square. So everything times 1 over k. So let's simplify this further. You end up with 2k square plus k plus 2k plus 1 divided by 6. This is the first term. Then this 2 and 2 cancels out. So you have k plus 1 square over 2. We have cancelled the k with the outside k also in the first expression. So this k outside is cancelled out with k. Okay, and this is the expansion of k plus 2 times 2k plus 1. And here also this k is cancelled out with this k outside. So you end up with k plus 1 square divided by 2, the minus sign. This k and this k will also cancel out. Therefore, you will end up with simply mu square. Okay, and we know that mu is k plus 1 over 2. So you can either replace this with simply k plus 1 square divided by 4. Right? Mu is k plus 1 over 2. When you square it, you get k plus 1 square divided by 4. Okay, so this becomes 2k square plus 3k plus 1 divided by 6 minus, by combining these two terms, we get 2 times k plus 1 square minus k plus 1 square again over 4. So that is the common denominator. So times 2 for this expression. What do we get at the end? 2k square plus 3k plus 1 divided by 6 minus. So 1k plus 1 square term will go away because 2 times 1. And k plus 1 square is simply k square plus 2k plus 1 over 4. Now let's take the common denominator of 6 and 4, which is 12. We get 2 times 2, so 4 times k square plus 6k plus 2 minus 3 times 4 is 12, so you have to multiply these terms by 3 with the minus sign. 3 times k square minus 6 times k minus 3. Okay, now if you simplify this further, you will end up with 6k, negative 6k cancels out. 4k minus 3k square is k square. 2 minus 3 is 1. So you end up with k square minus 1. But this is also the difference of two square terms. If you want, you can write this as k plus 1 times k minus 1 divided by 12. So both expressions are okay. So here's the variance of the uniform random variable when the possible outcomes of x is k. So if you go back to that example of tossing or rolling a balanced coin, rolling a balanced dice, a balanced 6-sided dice, we know k is 6, so the mean will be k plus 1 divided by 2, which is 7 over 2, 3.5, and the variance will be k square minus 1 over 12, which is 6 square minus 1 over 12. 6 square is 36 minus 1 is 35 divided by 12. So that is the variance. If you need the standard deviation, this will be the square root of 35 over 12. So you can easily find the mean and the variance of a uniform distribution. And when you know the PMF, which is 1 over k, you can easily find the probabilities for a given value of x. Okay, now we move on to the second widely used distribution, which is called the Bernoulli distribution. When an experiment contains only two possible outcomes, let's say a success and a failure, and the probabilities of these outcomes, where the probability of success is theta and probability of failure is 1 minus theta, then the number of successes 0 or 1 has a Bernoulli distribution. You can see that how you got these probabilities theta and 1 over theta. When probability of success is theta, the failure is its complement. Since the total probability is 1, the probability of the failure or the complement should be 1 minus theta. If you look at the definition of the Bernoulli distribution, a random variable x has a Bernoulli distribution and it is referred to as a Bernoulli random variable if and only if its probability distribution is given by x to the theta to the power x times 1 minus theta to power 1 minus x, and x can contain the values only 0 or 1. So 0 will be the failure and usually 1 will be the success. So if you find what will happen to the probability when x is 0, when x is 0, you have theta to power 0, which is 1, and 1 minus theta to power 1, which is 1 minus theta. This expression is when x equals 0. When x is 1, we have theta to power 1 and 1 minus 1 is 0, so this part is gone. So when x is 1, you get the PMF to be just theta. So if you combine the probability of success plus probability of failure, that will be 1 minus theta plus theta, which is the total probability 1. Here are some examples for Bernoulli random trials or Bernoulli random variables. You can define the success event to be getting ahead when you toss a balanced coin. Or it can be passing an exam. If you want it the other way around, failing an exam. Or it may be losing a race or winning a race. if you think about tossing a balanced coin, so you have only two possible outcomes. You either get head or tail. If you define your success event as getting a head, then your failure event will be getting the tail. But if someone wants to define the success event to be getting a tail, then the failure event will be getting a head. Therefore, depending on the way you define the failure and the success, you can assign the probability theta or 1 minus theta for these two events. An extension to the Bernoulli distribution is the binomial distribution. In Bernoulli random distribution, you have only one trial. That means you toss a coin only once. So you end up with either a tail or a head. But if you do this repeatedly, so that means a sequence of such experiments as repeated trials, which means if you toss this balanced coin many times, say 10 times, 15 times, then you end up with a series of successes or failures. If you want to model such a situation, then we go for the binomial distribution. That means a repeated trials of Bernoulli distribution becomes the binomial distribution. In order to define a binomial distribution, you have to satisfy three conditions. Look at these three conditions. The first condition is that the number of trials is fixed. Usually, the number of trials, we define it as simple or lowercase letter n. The parameter theta, that is the probability of success, is same for all of these n trials. That is the second condition. And the third condition, or the last one, is that these n trials are independent from each other. Again, if you satisfy these three conditions, then you can get the binomial distribution. That is, the number of trials is fixed, which is n. The probability of success is same for all these n trials, and these n trials are independent. So, for example, if you flip a coin 12 times, you should be able to find what is the probability of getting 5 heads if you toss a coin 12 times. Or you should be able to find what is the probability that you get more than 10 heads if you flip a coin 12 times. Or less than 3 heads if you flip a coin 12 times. So in order to answer these type of questions, you should be able to find an expression for the PMF of the binomial random variable. So if you look at the definition, you can find the PMF of the binomial distribution. A random variable x has a binomial distribution and it is referred to as a binomial random variable if and only if its probability mass function is given by n choose x, theta to power x, 1 minus theta to power n minus x. And x can contain values from, should be 0 up to n. Since we have n number of trials, our random variable x we usually define this as the number of successes. So our random variable x in a binomial distribution is the number of successes. If you have n repeated trials, you may end up with no success at all, only one success, two success, all the way up to maybe all of them are successes. So possible values of x will be from 0 up to n. You can write this PMF in another form like this. N choose x, theta to power x, 1 minus theta to power n minus x, when x contains values 0, 1, 2 up to n, 0 otherwise. So this is the most convenient way to write the PMF. In order to explain how we get this n choose x the combination. I'll show it using an example. Suppose you have n trials and your outcome is 1, 2 zeros, 1, 1, 0, 1, 0, 0 and so on. So we define 1 to be success and 0 to be failure. So if you look at these n trials, let's say our n is 20. Suppose you end up with 12 successes and the rest 8 failures. How many possible ways that you can have 12 successes and n failures? That means 12 ones and 0 eights. You may end up with 12 ones altogether and then the rest the 0 eights. Or you may have a success, a failure, a success, a failure and so on. 12 ones and 8 zeros. So if you think about these 12 successes and 8 failures, how you can have all possible arrangements of 12 ones and 8 zeros, then there will be n choose x possible ways. Okay, so you can choose out of 20, 12 ones. How can you arrange these 12 ones out of 20? So you have to consider all possible ways that you can have 12 successes and 8 failures. So all these possible combinations of 12 ones and 8 zeros are handled using this n choose x expression. So that is how you get the binomial PMF. And then the number of successes theta, you multiply it by 12, and the number of failures 1 minus theta, you multiply it by 20 minus 12, which is 8. So that is the second part of the PMF. Let's try to understand this by using an example. Find the probability of getting 5 heads and 7 tails in 12 flips of a balanced coin. So when you see an example like this, you already see that there are only 2 possible outcomes, that is getting a head or a tail. And you flip the coin 12 times, and you know if you toss a balanced coin, the tossings are independent from each other. You have only 2 possible outcomes, and at each toss the probability of getting a head or a tail is 0.5. So all 3 conditions are satisfied here. Number of trials is 12. Probability of success, which is theta, is 50% or 0.5 or 1 over 2. So the probability of failure is 1 minus theta, which is again 0.5. Okay. And our question is find the probability of getting 5 heads. So the number of successes, 5. If you use the expression or PMF, that will be probability x equals 5. We know that n is 12. Let's start with the definition. N is 12. 12 choose 5. Theta 2. Let's use our theta is 0.5. So let's use it here. 0.5 to power 5. 1 minus 0.5 to power 12 minus 5. Okay, so what is 12 choose 5? 12 factorial. 5 factorial over 7 factorial. 0.5 to power 5. 1 minus 0.5 is again 0.5 to 7. You can see the nice formation of this one. So you have the total number of trials 12, and at the bottom 7 plus 5 is 12, and this 5 goes with the success, the 7 goes with the failure. So this is easy. You can even remember this very easily. So if you do this calculation, you'll end up with, well, since you have 0.5 in both multiplications, you'll have 792 times 0.5 to the power 12, which is 0.19. What if you want to find the probability of getting x less than or equal to 10? What does that mean? Getting 10 or less heads, which means this will be getting no head at all, or getting one head, or maybe getting two heads, all the way up to getting 10 heads. How do you find this probability? So you have to apply this equation or this formula 0, 1, 2 up to 10, so 11 times. Okay, you have to apply this formula 11 times when x is 0, when x is 1, when x is 2, and all the way up to when x is 10. And then you have to add these answers together. Now this is going to be a very tedious calculation. But if you look at very carefully about this inequality, since there are only 12 possible trials, or 12 is the number of trials, if you look at the complement of this, okay, so the possible values of x is from 0, 1, 2, 3 up to 12. When we need x less than or equal 10, we need all these figures 0 up to 10, and you see this is the complement. Now can you guess how we are going to do this example? We look at the complement. Probability x less than or equal to 10 is same as 1 minus probability x greater than or equal 11. Can you see that? So this is the complement. So you have 1 minus. Now your complement contains only two possibilities. That is either x equals 11 or x equals 12. So you have to apply this formula only twice, and that can be easily calculated. So you have 12 factorial, 5 factorial, 11, should be 11 now because x is 11. 11 factorial, 1 factorial, 0.5 to power 11, 1 minus 0.5 to power 1, plus when x is 12, you get 12 factorial, 12 factorial over 0 factorial, 0.5 to power 12, 1 minus 0.5 to power 0. You can easily calculate these probabilities. Not only that, if you want to find a probability that the number of heads you get lies in between, say, 4 and 6. So that will be the probability x equals 4, x equals 5, and x equals 6. So you have to apply this formula 3 times when x is 4, x is 5, and x is 6, and add them together. Now if you look at this example carefully, when your number of trials 12, it's easy to handle, and the probability of success it's 0.5, and that calculation is also very simple because the probability of success and failure are both same. These calculations are easy. You can do the hand calculation using a standard calculator. But what will happen if you end up with your n to be very large and your theta not that much easy to handle? So we do not use the hand calculation or this formula all the time. In order to answer this type of questions, you can easily use the available binomial table. Say for example, find the probability that 7 of 10% will recover from a disease if we can assume independence, and the probability is 0.8 that any one of them will recover from disease. Okay, before we look at how to use the table, we'll see how we can do this in the usual way. If you read the question, the first thing you have to do is identify the parameters. Okay, the parameters are the values that define your PMF. In binomial random variable or binomial distribution, you have two parameters, that is n and theta. That is the number of trials and the probability of success. So when you read your question, you have to figure out what is your n, what is your theta, and what is x. You have to find the probability that 7 of 10% will recover from a disease. So there are 10 altogether, and the probability is 0.8 that any one will recover. Any one of them will recover from the disease. So your success event is recovery, right? And that probability is 0.8 or 80%. And you need 7 out of 10. So x is 7. If you apply the formula, for probability x equals x, in our case it is the probability x equals 7, n is 10, x is 7, theta is 0.8 to power 7, 1 minus 0.8 is 1 minus 0.2 to power 3. So you can easily find this answer. But look at this one. If the response rate for a mailed questionnaire is 15%, find the probability that 35 of 80 persons will respond to a mailed question. Now in this case, x is 35, so which means you have to do the calculation with n 80 and theta 0.15 with x 35. What if you have to find what is the probability that at least 35 of this 80 will respond to a question, or at most 40 out of 80 will respond to a question? Now adding this formula 40 times, 41 times, 35 times, it is not practical at all. So we'll see how to get this type of questions done using a binomial distribution table. Now you can see a part of the binomial distribution table. Now this is the cumulative probabilities or distribution of the binomial random variable. If you look at this table closely, you see the first row contains the probability of success. There are possible probability of successes you see here, 0.01, 0.02, 0.03 up to 0.5. And the number of trials, actually n, so it's better if you name this as n. When number of trials is 2, 3, 4, 5, 6, and this table will continue. So usually available tables contain some defined probabilities of successes for some n values. Maybe not all of them, but there are online calculators or even software that you can easily find the binomial probability for given p for given n. Let's look at one column or one subtable in this binomial distribution chart. Look at when n is 5, that is the number of trials is 5. So possible values of x will be 0, 1, 2, 3, 4 up to 5. And depending on the probability of success, you can find the cumulative probabilities. See, you can easily understand it because when x is 5, that means that's the total probability. When you have the cumulative probabilities, you add the probability at each and every value cumulatively, and at the end you attain the total probability 1. So this is the CDF. Say for example, when n is 5 and probability of success theta is 0.2, you find the correct subtable, then you find the correct column for your probability of success. Now in this case it is 0.2. So you have to look at this column for the table 0.5. So these are the probabilities you need. So 0.3277 is probability x equals 0. 0.737 is the probability x less than or equal to 1. Remember, this is the cumulative density. So 0.7373 is not x equals 1, but that is x less than or equal to 1. This is when x less than or equal to 2. That means probability of x equals 0 plus probability of x equals 1 plus probability of x equals 2. All of them. So this is the cumulative probability. So likewise, you have this is x less than or equal 3, x less than or equal 4, x less than or equal 5, and so on. So you had attained the total probability 1. If you know how to read this table correctly, you can easily calculate the probabilities without using this formula all the time. So it will save time and it is very easy. Okay. So let's do a complete example and see how we can use this table to find probabilities. So here's our question. A quiz contains 15 independent multiple choice questions where there are 5 options or answer options and only one option is correct. Suppose a student is going to guess the answer for all these 15 questions. Suppose he forgot to study for the quiz, so he's going to guess all the answers. Now, how many independent questions are there? There are 15. So, number of trials is 15. What is the success probability? A success is getting the correct answer. It says that there are 5 answer choices, that is A, B, C, D, E. So it is a multiple choice question, only one will be correct. So if there is only one correct answer, the other 4 are wrong answers. So the probability of selecting the correct answer is only 1 out of 5. So your probability of success is 1 out of 5. Okay, or which is 20% or 0.2. So you have to figure out by reading this question what is your probability of success. Although it is not given straight away, the information is all provided. There are 5 answer options, only one is correct. So probability of getting the correct answer is only 1 out of 5. Now let's see what is the probability. Now this student is going to guess. What is the probability that out of these 15 questions that he will get less than or say 7. He get answers for less than or equal to 7 questions. Okay, maybe no correct answer, maybe only one question he got correct, or maybe 2, maybe 3, all the way up to 7. So what is the probability that your x here is now number of correct answers out of 15. Okay. So x less than or equal 7. So you get the binomial table and you find the correct subtable for n equals 15. So here's my n equals 15 table. So you see the part of the n equals 15 table here, so you don't need it. Here's my n equals 15 subtable. So this is what I'm going to look at. And the probability of success is 0.2. So you select the column 0.2. So usually in tables they use P as the probability of success. So this is the P is actually the theta, another symbol. Okay. If you need Px equals 7, you just read the 7, that row, and you find it is 0.9958. So this is very easy to read the table. Now what is the probability that he will get less than 7 questions without the equal sign? What is the probability in that case? So he get less than 7. So this is same as less than or equal 6, right? Less than 7 means 0 up to 6, 7 not included. So it is same as x less than or equal 6. So you read the row for 6, you find it 0.9819. Now what will be the probability that he answers 7 questions, exactly 7 questions correct? Exactly 7 correct answers. How do you find that? You don't see the answer in the table, but you have to find it using a small calculation. You know that p equals 7 is, if you read the probabilities all the way up to 7, less than or equal to 7, and subtract less than or equal to 6, then you get what is px equals 7. Which means, so you have the possible values of x, 1, 2, 3, 4, 5, 6, 7, 8 and so on. If you want to find 7 only, when you read the table up to 7, you get the probabilities of 0 plus 1 plus 2 all the way up to 7. But you want only exactly 7, so you have to get rid of this unwanted stuff. That means all the way from 0 up to 6. So what do? You read the table up to 7 and then subtract the unnecessary probabilities. So this will be, you read the table all the way up to 7 and subtract the unwanted probabilities, 6. So that will give you 7. Okay, so you read the table up to 7, which will be 0.9958. Then you subtract the unwanted stuff, which is, you already know it is 0.9819. If you do this subtraction, you get exactly what is x equals 7. So this is very, very easy. So this is x equals 7. If you look at this table, you have 0.9958 and subtract the 1 exactly above it. Right? So this is very easy. Let's try another one. What about px equals 4? How do you find this one? So you need only 4. If you read the table up to 4, you get everything from 0 up to 4. Or you need only 4, so you have to get rid of this unwanted 3. So you read up to 4, subtract everything up to 3. So what is the answer? Here's 4.8358. Subtract the one about it, 0.6482. And you'll get the answer 0.1876. So I suggest you try these calculations by yourself. Okay. What about if you want to find the probability that this student will get more than 6 answers correct? More than 6 correct answers. So x greater than 6. So what does that mean? Here are the possible values up to 15. Greater than 6 means 7 or more, right? You don't see the equal sign, so it is 7 or more. How do you read this from the table? Now remember, in the cumulative probability density table, not only the binomial table, but there are many other available cumulative density tables. It always gives you the cumulative density from your left side up to whatever the number you have. Everything from 0 up to 6 or 7 or 8 and so on. So if you need the complement, now this is the complement. You have to do the 1 minus calculation. Okay. So if you need 7, 8, 9 up to 15, so here's the complement and this is what is available in the table. So you read up to 6 and do 1 minus. Right. So if you read up to 6 and when you do 1 minus that, you get the complement. So again, this is not that much hard. So where's your 6.9819? So do you do 1 minus? You get the probability 7 up to 15. What about probability x greater than or equal 4? How do you find this probability? Now these are two different things because you have the equal sign here. right? So you have the equal sign here. So here are the possible values, goes up to 15. You need everything greater than 4 and above, everything. So you need 4, 5, 6 up to 15. Now what is your complement? 0 up to 3. 0 up to 3. So where's 3? Here's 3. 0.6482. So you do 1 minus 0.6482. I hope this is very clear to all of you. Not only that, you can find probabilities like in between probabilities, say x in between 3 and 7. How do you find this one? So here are the possible values. Goes up to 15. You need 3 up to 7, including them. See the equal sign. So you need everything 3, 4, 5, 6, 7. Now how do you read the table? If you read up to 7, you get everything from 0 up to 7. Right? Then you have to get rid of unnecessary values. So unnecessary values will be 0, 1, 2. If you subtract 0, 1, 2, you can get what you want. Only 3, 4, 5, 6, 7. So you have to do the subtraction x all the way up to 2. So what is that value? Up to 7 you have 0.9958. Subtract up to 2. So 2 is 0.3980. And you can find the answer. What if you need probability 3 less than x less than or equal 7? Now you see the 3 is not included here. So what are the values you want? You don't have to write these possible values of x all the time. Okay, I am showing it just to make it clear. If you can easily figure out how to get this equation, you can straight away write it. You don't have to write this 0, 1, 2 up to 15 all the time and mark it. You can easily, with the practice, you will easily get this by your mind. Okay, you don't have to do this selection all the time. So you know it is from 3 not included, so 5 up to 7. So which means you read the table up to 7 and you subtract the unwanted stuff. Now 3 is also not wanted, so you have to subtract up to 3. So read these two values from the table and you are done. Okay. So I'm sure that it's clear how to read the table now and answer the questions. The first thing you have to do is when you read a question related to binomial distribution, check whether the 3 conditions are satisfied. Identify the parameters, those are n and theta. Then out of the available tables, figure out the correct subtable for n. Figure out in that subtable what is the column for your corresponding probability of success, that is theta. And when you have that column, you can answer any question related to the probabilities. Okay. Now if you look at this table, you see that it goes only up to 0.5. What if you need probabilities greater than that? What if your probability of success is 0.4 or 0.8 or 0.9? You don't see that table here. You don't see those columns here. Now it is always not possible to provide all possible theta values because there can be many. Okay. But using this table from 0 up to 0.5, you can easily find the probabilities for theta greater than 0.5. Here is the formula that you can use for that. Theorem 5.1. So this bxn theta, this is the notation that we use for the binomial probability with number of trials n and probability of success theta. This bxn theta is same as bn minus x n minus 1 minus theta. So this is the complement. So here's the formula for the success, and here's the formula, the same thing written using the failure, but these two are same. So let's try to prove this one and see how that failure probability and success probability can be used both ways around. Okay, let's start with the left hand side. B x n theta, which is n choose x, theta to x, 1 minus theta to n minus x. And the left hand side is n minus x, n, now 1 minus theta. So let's rewrite this formula. Now it is n choose n minus x. And our success probability is now 1 minus theta to power n minus x. So 1 minus theta is theta, n minus, theta to power n minus x. So it's the same thing now, okay, with replacing n with n minus 1 and theta with 1 minus theta. Okay. Now let's see what is n choose n minus x. That will be n factorial, n minus x factorial, n minus x factorial. So if you simplify this, you will see that this is n factorial, n minus x factorial, and cancels out. Negative and negative, we get x factorial. So this is same as, which is ncx. So you see that n choose n minus x is same as n choose x. Simply if you say n is 10 and x is 3, n choose 3 is same as, 10 choose 3 is same as 10 choose 7. Okay, because this is 10 factorial, 3 factorial, 7 factorial, and this is 10 factorial, 7 factorial, 3 factorial. This is a multiplication, so you can interchange 3 and 7. And you see that this is same. Okay, n minus x is same as theta to x. So these two parts are same, and if show that ncx is same as n minus x, so you'd have the answer in your proof. So which means bxn theta is same as bn minus xn 1 minus theta. Okay, so if you want to find the binomial probability of 7 when number of trials is 10 and probability of success is 0.8. In your table you don't have 0.8, but you have the complement, which is 0.2. So that will be same as 10 minus 7 with number of trials 10, but with 1 minus 0.8. So that means if you read the table with x3 and number of trials 10 with probability of success 0.2, you get the same answer. Right? You get the same answer. So this will be probability. You're finding x equals 7 with theta 0.8 is same as finding probability of x equals 3 with theta 0.2. So you get the subtable for n10. You don't have 0.8 column, but you have 0.2 column. If you want to get the probability x equals 7, you read only up to x equals 3. So which is x less than or equal to 3 minus ex less than or equals to 2. Okay, so I refer the table and find the answer for this one. Next we look at how to find or derive the mean and the variance of the binomial random distribution or binomial random variable. The theta can be represented as n times theta, sorry, the mean is represented as n times theta and the variance as n times theta times 1 minus theta. This is very easy to remember. Okay, let's try to prove this one. So let's start with the mean. Mean is e to the x. So that is x going from 0 to n, x, n choose x, theta to x, 1 minus theta to n minus x. Okay, so this is xpx, sum of xpx. Px is, here is the PMF of the binomial density. Yes, x times px. Okay. When x is 0, what will happen? When x is 0, you have 0 times this whole expression. So the value when x is 0 is 0. So you can omit it and write only from 1 to n. Because when x is 0, this whole thing is 0. So you can write this as the summation from 1 to n. Okay. So here's the combination. And then you get x goes from 1 to n. This x, and if you simplify with x factorial here, right? So you get x times x minus 1 factorial. So this x can cancel out, right? So that's one trick that you can use. You know, x factorial is what? X times x minus 1 times x minus 2 all the way up to 1, right? So you can write this as x times x minus 1 factorial, right? So this x at the top you can cancel it out. And you have the rest theta to x, 1 minus theta to n minus x. Okay. So you have already omit x equals 0, which is 0, right? Now let's see what we have here. So our mu is you can take 1 theta out. Okay. So here's another trick. You have to rearrange these terms sometimes. Okay. So it corresponds with something we know. Now if you look at these factorial terms, you have x minus 1 factorial and n minus x factorial. So if you can have these two terms in theta also, that means it becomes that binomial PMF. But you have theta to x. If you can make this theta to x minus 1, then you can easily rewrite a binomial formula, another one. So what we do is we take 1 theta out and write theta x minus 1. So theta times theta x minus 1 is theta x. So nothing has changed, just rewriting a term in a different way. And you know theta is it's a constant, so you can take that out. And also, instead of n factorial, because if you add x minus 1 and n minus x, what do you get? You get n minus 1. So if you can have n minus 1 at the top, right, n minus 1 at the top, then that is also something nice because we can get the binomial expression. Okay, I'll show you how that comes at the end, but just look at what I'm doing. So I made theta x to be theta times theta x minus 1, and let's do the same with n factorial. Rather than n factorial, I'm going to write n times n minus 1 factorial. It's the same thing, right? It's the same thing. N times n minus 1 factorial is n factorial. So you can take n and theta outside. So now your mu becomes n theta times the rest of the summation. And we have theta to x minus 1, 1 minus theta to n minus x. So your mean is n theta times x equals 1 to n. Now this is n minus 1 choose x minus 1. Okay, so see whether you can get this one. N minus 1 choose x minus 1. So this expression. And you see that you have theta to x minus 1, 1 minus theta to n minus 6. Now this is something very familiar because, okay, so let's make x minus 1 to be y and n minus 1 to be m. Let's see how your formula now look like. Mu is n theta, x goes, and my x is y, okay, sorry, y is x minus 1, so x equals 1 will be y goes from 0 to m now, okay. Instead of n minus 1, I write m. Instead of x minus 1, I write y. So you get theta to y, 1 minus theta to m minus y. When y is 0, x is 1, right? And using this substitution, your summation x from 1 to n becomes y from 0 to m. So take your time and study this summation after replacing y with x minus 1 with y and n minus 1 with m. This expression you have here is same as the expression you see here. They are the same thing. So take your time and study it and make sure you understand how we got this expression from the previous one. Okay. Now what do you see here? What is this? This is again the PMF of a binomial distribution. PMF of the binomial distribution where number of trials is m and probability of success is theta still. Okay. And if you take y from 0 to m, that means all possible values of y, this is the total probability and this goes to 1. Okay. So this is the sum of px for all x's. You know that is the total probability 1. So this whole thing becomes 1, which means your mean is n times theta. So that is how you prove that the mean of the binomial distribution is n times theta. Now in this proof, you have learned several tricks how to rearrange terms according to an expression that you want at the end. So you have to plan this very carefully. You should have in mind where you should end up with. Okay, and depending on that, you have to arrange the factorial terms, you have to arrange the theta terms. Okay, there are several tricks that we have used with the factorials, rewriting the factorials, taking constants out, and making a summation or an expression inside the summation which is a well-known probability distribution. So you end up with another binomial distribution with another value for m, another value for y, but they are related to x and n, the original parameters. Rearranging these type of things or rearranging the terms in this way, you can easily prove the mean. So study these steps very carefully and be familiar with these tricks because you will be using them a lot in future. Okay. Right. Now we'll see how we can find the variance. You know the variance is the expectation of x square minus ex whole thing square. Okay. Now ex square can be written as expected value of x minus 1 plus ex. So here's another trick. Okay, if you expand this, you'll get this one. So the expected value of x times x minus 1 is what? Sum x goes from 0 to n, x times x minus 1, and choose x, theta to x, 1 minus theta n minus x. Ex we have already found it. Okay, so we'll forget about it for a while and come back to it later. But we'll look at this expression, expected value of x times x minus 1. Okay. When x is 0, this whole expression goes to 0. When x is 1 also, this whole expression goes to 0. So when x is 1, you have 1 minus 1 here. So when x is 0 and x is 1, the whole expression is 0. So you can omit that from the equation. Now you can get only the summation goes from 2 to n, and x times x minus 1 is there, and you have n factorial x factorial n minus x factorial theta to x, 1 minus theta to n minus x. Now here again we can get rid of x and x minus 1 by rewriting your factorial term like this. You can write x times x minus 1 and then the rest as the factorial. And you have n minus x factorial, and at the top the same thing. Why I do this? Because I can cancel this. Okay. And also we do the same trick again. N factorial, we write it as n times n minus 1 and then n minus 2 factorial, because x minus 2 and n minus x, if you add them together you get n minus 2. So you can rearrange the terms so that you will end up with another binomial density. And again you have to do the trick. That is the trick. Theta and theta square. Sorry, it's better to write. I'll write it like this. Now since you need x minus 2 for theta, okay, you need x minus 2 to theta. So if you write it like this, this is same as theta to x, right? Theta square times theta x minus 2. If you multiply them, you get theta to x. So it's the same thing. Why do we do that? In order to have theta to power x minus 2 term here, because then it has that nice formation of the binomial density, right? Now you can take the constants out. Your constant will be now n times n minus 1 times theta square, okay? And then by replacing x minus 2 with y and n minus 2 with m, like the previous case, what do you get? Expected value of x times x minus 1 becomes, here are my constants taking outside the summation. Instead of x, now we replace it with y. When you replace y equals x minus 2, you get the summation going from 0 to m. And then you get m factorial at the top, because n minus 2 is m. Okay, so you get m factorial. X minus 2 is y, so you have y factorial at the bottom, and then m minus y factorial. Theta to power x minus 2 is y. 1 minus theta n minus x will be m minus y. Now what do you see here? Another binomial density. Okay, so you see sum of y going from 0 to m. M choose y, theta to y, 1 minus theta, m minus y. So this is the binomial, okay, with m number of trials, okay, for the variable y. And if you do the summation of all possible y values, this goes to the total probability 1. So your answer is just n times n minus 1 times theta square. Okay, we are almost there. So go back to our variance term. Yes, our variance term, we have found an expression for ex times x minus 1. We already know the formula for ex, which is mean, which is n times theta. So let's replace these values to our variance term. Okay. Right. So our expected value of x times x minus 1 becomes n times n minus 1 theta square minus n theta. This is ex, right? And we know the variance of x, or sigma square, is ex square minus ex all things square. Okay, and ex square is actually this one, right? So let's replace it. N times n minus 1 theta square plus n theta. Okay, let's double check our expression. Okay, so we have the plus sign here, sorry. So we have plus sign here for ex square term. And then minus ex is n theta, it's whole thing squared, like this. Okay. So you end up with n square theta square. Okay, this expansion, and then minus n theta square. So this is the expansion of this term, plus n theta minus n square theta square. This cancels out. We end up with n theta times n theta square. So take the common factors out, you get 1 minus theta. So this is exactly the variance of the binomial random variable. Okay, so these two proofs, the mean and the variance, it explains a lot of many new things, especially how to deal with summations, rearranging the limits, rearranging terms with the factorial terms, so you can come up with a well-known formation of another binomial distribution. So please refer these proofs, these steps thoroughly, take your time and try to understand it properly. Okay, in the next session, we'll look at how to find the moment generating function of the binomial distribution.